Okay, so this is the first pass at the talk that I'm giving for Summit. I want to get this down and record it so I can see how this works. All right. So thanks everybody for coming out. My name is Casey Stella. I'm going to talk to you about streaming outlier analysis for fun and scalability. So we're in the IoT section, but I'm going to talk to you about a streaming algorithm that works well for IoT as well as for streaming analytics, sort of more traditional streaming analytics. Okay, so first we're going to talk about streaming analytics, then we're going to talk about the framework that we've constructed, and then we're going to give an example. I'll show a couple of examples. Okay, so my name is Casey Stella. I'm an engineer at Hortonworks. I work on the Apache Metron project. That's a cybersecurity project. That means that we're dealing with streaming data, doing streaming threat intelligence, streaming cybersecurity. Before that, I worked in the professional services organization as a data scientist. I'm currently a data scientist on the Metron project. Before that, I worked in healthcare doing Hadoop. I worked in the oil industry, mostly doing data science, software engineering, almost always in the big data space. Okay, so streaming analytics. A couple of things I want to point out. The future involves non-trivial analytics done on streaming data. Before, if you've gone to Hadoop Summit, you heard a lot about batch analytics, and that's not going away. But I think that you're going to hear more and more, and we have heard more and more about non-trivial analytics done on streaming data. To date, we've focused a lot on more along the lines of the simpler analytics, counting things, getting an idea of when things get past a certain threshold. Even with outlier analysis, which is what I'm going to talk to today, a lot of the use cases that I see are people saying, if my values go past this threshold, then I want to trip a sensor, or I want to trip an alert. Right. The other thing I want to point out is this is not just IoT. Traditional streaming analytics needs non-trivial algorithms. It needs more of the data science love inside of streaming. Because there's a need for the insights to keep pace with the velocity of the data. The data is coming in really, really fast. And most of the time, the real value add around Hadoop and the real value add around all of this stuff, streaming in general, is that you can increase the signal-to-noise ratio. Right? It's not cutting a human out. Rather, it is making it so humans have to look at fewer data points in order to make good decisions. So it's not automatic insights, but it's automatic intelligent filtering so that humans can make better insights. Okay, so the good part about streaming analytics. Much of the data can be coerced in a time series. Much of the data has a format, right? A lot of times, especially around IoT, we're gathering a sensor at a certain point in time, or at a certain rate in time, every second, every 5 milliseconds, every hour, every day, etc. The problem is there's a lot of data, and it's really coming fast. Especially, I'm not going to tell you how much data there is. Lots of people have talked about, how big IoT is and how big streaming data is. Data velocity and data volume is increasing dramatically. The other nice thing is outlier analysis or anomaly detection is a killer app. So most of the time in this streaming data, because it's coming at us really fast, we need to know what to look at. We need to know what to concern ourselves with. So examples of outlier analysis, things like fraud analytics. You want to know whenever something is outside of a certain bounds. If I'm here in Dublin and I use my credit card, and all I've been using this credit card for is, buying a scone or buying, a coffee here and there, and all of a sudden a $10,000 purchase comes up. Well, maybe there's something wrong. But more importantly, and the same thing happens with sensors, right? If a temperature sensor spikes, or it behaves abnormally in some way. That is outlier analysis or anomaly detection. Problem is, outlier analysis is, one, difficult to do, and two, computationally intensive. So you'll notice that over the course of the last couple of years, a number of the large web properties have written blog posts around how to do outlier analysis. Netflix alone has 2 of them. I've seen one from eBay. It's a hard problem. There's not a lot of solutions out there, but we're going to talk about one today. The good, there's no shortage of computational frameworks to handle streaming. So a lot of the computational primitives are there, and you don't have to reinvent them. You have Storm, you have Spark Streaming. To a certain extent, you have NiFi. Actually, to a large extent, you have NiFi. That is very good. You don't have to reinvent the wheel on some of the really difficult engineering problems. The problem is there's not an overabundance of high-quality outlier analysis frameworks that plugs into that. So if you just try to plug in a batch-style outlier analysis framework that requires all the data and is n-squared and extremely memory-intensive into these frameworks, what you're going to do is it's a recipe for just falling over. It's not scalable fundamentally. So what we need is a solution to this particular problem, and that's what I'm hoping to solve today. So we're going to talk about how to differentiate interesting points from normal points. One of the nice things is Macrobase just came out, which is a system built in collaboration between MIT, Stanford, and Cambridge Mobile Telematics. And they noted a few properties in their paper. It's around IoT, it's around outlier analysis. They do a little bit different than what I have done here, but the approaches sort of rhyme. They are not doing this on Hadoop. They're trying to scale on a single node. But the ideas are very similar. So one thing they do note about several properties of IoT data. Data produced in IoT applications often comes from some ordinary distribution. So traditional approaches to outlier analysis that are statistical or use robust estimators actually can work and do work fairly well, which is good news. The other thing is IoT anomalies are often systemic. So if a temperature sensor fails over here, it's generally going to have a cascade, or if something goes wrong, it's going to have a cascade across multiple sensors. The other thing is, at least for healthy machines and for healthy data sets and for healthy processes, the IoT outliers should be relatively rare. So we shouldn't have to worry too much about the challenges around false positives. I urge you to look at Macrobase. It's macrobase.io. Their paper here is quite good. It's very interesting. I'm actually using a little bit of the same techniques, especially their sampling approach. I think it's quite good. But what we're going to propose here, or what I'm proposing here, is a hybrid approach for outlier analysis. So before outlier analysis, really, the best that you often saw was, we're going to gather samples as data streams by, and then we're going to do, for every point, we're going to run it past a really, really intensive outlier analysis algorithm. That just does not scale. It doesn't work. Those, even on a small sample, if it takes you upwards of a second to determine at every point if it's an outlier, and you're getting data in every 100 milliseconds, that's not going to work well. Right? So instead, we're going to use sketching algorithms to make a first pass. So for every data point, we're going to detect outliers using a robust estimator of variability that uses distributional sketching. So in particular, we're going to use median absolute deviation, which is nice because while it does assume certain distribution, while it does assume a certain distribution about the data, it is quite robust, and it has been shown to work very well on real data. But instead of gathering the traditional challenge about median absolute deviation is you had to compute the median, and the median requires a sort generally. But with advances in distribution and sketching algorithms, so that meaning getting an approximate idea of the distribution and an approximate median, you can get, using Q-trees, you can actually get a sense of the distribution. And if you can get a sense of the distribution, you can get a sense of the median. So what we're doing is every data point that's passing through, we're adding it to our distributional sketch, and we're determining whether or not that point is an outlier or an outlier candidate based on the median absolute deviation. So the median absolute deviation, just in short, takes the median of the difference between every point and the median, right? And if that value, from there you can construct a z-score, and if that z-score is more than some threshold, you can you would indicate that it's an outlier threshold, or you would indicate that it's an outlier candidate. From there, once we've gathered it's an outlier candidate, we can then pass it by a second pass. But before that, we're actually going to gather a biased sample. So we're going to bias it towards time, right? So more recent points have a higher probability of showing up in our bias, or in our sample. So the benefit of this is it's extremely deterministic in space and very cheap in complexity, right? In terms of computational complexity, it's pretty much constant in space because we're just keeping a reservoir sample, a biased reservoir sample of the data passing by, as well as the distributional sketches, which is constant memory and constant CPU. Right? So from there, once we have our candidate, then we can use the more traditional technique on our sample, right? And the one that I've chosen is actually the one that Netflix chose originally in their first outlier analysis blog post. It's a robust PCA. So I'm not going to necessarily get into the weeds on that. And if you want to, you can look at either the source code, or you can look at the very good blog post about from Netflix. But the idea is that robust PCA is nice because as you reduce the dimension in the PCA, you can look at with and without each of the different vectors. You can see how the projected space looks, and you can kind of determine in the sense of, if you add this particular vector, does it really churn the projected space? And if it does, then that point is probably not from the original distribution of the other points, right? So, right. So from there, that's expensive computationally, but it's run on a sample and it's run infrequently. So again, it's still deterministic, for the most part deterministic. Obviously, it depends very heavily on how loose your first pass filter is, right? If you pass everything as an outlier candidate and your threshold's 0, right, you're going to run this on every point, which you probably don't want to do. Okay, so this becomes, in effect, the way to think about this is it's becoming a data filter, which can be attached to a time series data stream within a distributed computational framework like Storm or Spark or Flink or NiFi to detect outliers. Right now, there's a Storm implementation, but the core implementation is split from the individual computational framework. There's a core project as well as a Storm project right now. In the future, I'll be implementing the same thing for Spark and Flink. Actually, those Spark and Flink can actually use the code itself. It's fairly self-contained. And I'll be doing some helper methods for NiFi as well. Okay, so we're going to go into a demo real quick. And from here, we're going to talk first about temperature sensors. So this is data that was gathered from an outlier detection benchmark from Numenta. And we have a device, and it's a sick device, unfortunately. So I'm going to pass this back to 2013. Actually, before I go into that, let's go into the architecture of what led us here. So how this works from an architectural perspective is we pass data from Kafka, which is what's capturing, which is where your sensor is putting the data. Probably a NiFi implementation here, pushing the data into Kafka. from within the Kafka spout, we're splitting these things by groups. You can group things together and just do the outliers on a given group. So this will become more important when we talk about some of the other examples, but you can kind of see for this situation, it's a group of one. So another example of a group might be like a machine ID, right? You only want to look at outliers within that machine, for instance. And there it's passing through our outlier bolt, which is entirely self-contained. And that outlier bolt is pushing the data into OpenTSDB, the raw data. So that's every data point, and pushing just the outliers into the Elasticsearch persisting bolt, which gets persistent to Elasticsearch. And from there, these two data stores are used as input into Grafana to gain my insight, because what I really need is dashboards at the end of the day, because a human has to look at this. Okay, so let's look at Grafana, the Grafana output for this. So here's my machine sensor. He's sick. Let's look at this guy. Okay, so the yellow points are outliers, and the green points are just the regular data points. So you can see what's happening here in this machine is he's varying, not a ton, some. All of a sudden, he spikes up. And then something is just kind of going wrong here, and they have to bring the machine down. You can see the outlier detection algorithm is finding these data points on the way down, but it's also finding the data points on the way up. And it's also finding these data points, which are the result of a lot of churn. So the frequency is shifting here. It's oscillating between temperatures in a way that's kind of abnormal. So as it goes forward through the year, it's varying, but it's mostly staying within certain bounds. It's detecting outliers when it gets kind of on edges here, above this edge, below this edge. Right? Median absolute deviation and pretty much any outlier analysis wants you to stay on average, wants you to oscillate around a point or around a line. Right? So once it gets here, it's starting to dip and act erratic, more erratic. And by the time it gets here, it's acting quite erratic indeed. So it's spiking and going up and down. And at this point here is when things start to really go haywire. So on this dip, it starts to have tiny oscillations, and finally, large oscillations, which results eventually into the machine crashing here. So what you want is for humans to look at this and to understand at this point that things are starting to go wrong. Things are starting to go haywire. So this is a nice dashboard because you can kind of get to see the overall picture as well as slice and dice. I can slice a time series, and these are just the outliers. You can see the temperature and how much of an outlier it is. Right, so at 127, around 130 or so, it's really quite an outlier, right? And you can see that you can see the percentile to kind of get an idea, an estimate. At 62 degrees, that's substantially lower than the 99th percentile of the window back, right? Which is over here. So that's probably around here, more than likely. Is it 125 right here? So at this point, it's very different than the window back, right? Okay. So the idea is that you can investigate these things. Every day you should be looking at these things whenever there's an outlier triggered. So in addition to physician sensors, in addition to temperature sensors, we can also look at a more traditional fraud use case. Okay, so physician fraud. So as part of the federal government's requirements, as part of the Sunshine Act in the United States, we have to list the financial relationships between physicians and providers of, and essentially companies in the medical industry. Right, so any gifts that happen, they have to be noted. And there's an open data set that's released every year. The idea is that you probably don't want to look at the open data set at the end of the year. You want to look at the data as it's coming along, right? And I've given talks about this data set before. It's a really interesting one. So what we're going to do is we're going to look at this data from what you have here at the top is a list of all of the outliers sorted by the score to which we believe that it is an outlier, right? And this isn't getting me the whole data. Hold on a second. Let's see here. We'll get all the data. There we go. Okay. All right. So if we're looking at just gifts, we can look at gifts or travel and lodging. Those are the two kind of interesting reasons. We can further segment by the physician specialty. So we don't want to necessarily consider just the outliers across all physicians, because certain physicians have different relationships with industry, right? People who create prosthetics will have a deeper consulting relationship and contracting relationship with industry than, say, for instance, your primary care physicians of the world, right? So what we want to do is, for a given reason in physician specialty, we want to look for outliers there. So this is a list of all the outliers oriented, or rather sorted by the real outlier score. So for here, we have a dentist here, a prosthodontic dentist. And what we're going to do is we're going to look for that guy. Let's see what that particular outlier looks like. I don't think that was the right one. Prosthodontic dentist. There we go. So you can see here, the yellow is all of the dentist payments. These are individual payments, all right? This guy is our dentist in question, the green. He sticks out like a sore thumb. So what is that going on? What's going on there? Well, actually, the data set has some context around it. Evidently, he received a surgical kit, a surgical implant kit at no charge per consulting agreement. So he had some sort of barter situation going on with a dental supply store. But as a result, it popped up right there. So if that relationship is erroneous or fraudulent or interesting in some way, you want to be able to look at this guy individually, right, and have it pop up. So let's look at, instead of the dentist, let's look at our eye doctor, right, an optometrist. Okay, here's our optometrist. That's fairly big, right? A $12,000 payment from Carl Zeiss Meditech to this physician with this ID, redacted at this time. So let's look at what this looks like in concert with his peers. So you can see the 99th percentile of payments for this particular type of doctor is $384. He got paid around $13,000. That's a lot of money. That's definitely outside of the normal distribution here, or rather, that's outside of the norm, and something that should be considered, right? Something that should be looked at further. So you can see dentists are actually very often the people that we do look at. So if we want to, we can see we can look at travel and lodging. Okay, so for travel and lodging, a lot of it is psychiatric and neurology, orthopedic surgery. Right. So let's look at the psychiatric and neurology. Actually, neurology. This guy. Okay. So we've got a few outliers here, right? So we're looking at this particular one at 1219. So we're going to zoom out. Okay. Let's zoom into 1219. This guy right here. All right, what does he look like? Looks like there's a couple of points here for the same doctor, one for $38,000 and one for 9.4K. And he's a physician contractor that worked in the clinical development department at Biogen between April and December. So what you can see here is there's good reason for this, right? Some of these are good reasons, some of these are strange reasons. What you want to be able to do is have a solid way to filter and look at, differentiate the situations that are abnormal, and then look further into them. Because no machine is going to necessarily be intelligent enough to say, oh, okay, this makes sense. A human is going to have to be the one doing that. Okay, so from there, we talked about the architecture. From there, I'll take your questions. All the code and scripts are here on my GitHub account. I'll be refining this and building better instructions and documentation and things like that over the course of the year. I think this is an important piece of software, and I think it's really a nice use case to show off IoT for IoT and streaming analytics. So I'll take your questions. Thank you.